Introduction to TCP Window Scaling. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into TCP Window Scaling, a critical TCP enhancement that enables high-throughput data transfers across modern networks. This topic is essential for anyone working with network performance optimization, cloud infrastructure, or high-speed data transmission. TCP window scaling was introduced to solve a fundamental limitation in the original TCP specification. When TCP was designed in the early 1980s, network speeds were measured in kilobits per second, and the designers never anticipated networks capable of gigabits per second or the high-latency links we have today with satellite and intercontinental connections. The original TCP header allocates exactly 16 bits for the window size field. This means the maximum value that can be expressed is 65,535 bytes, which equals 64 kilobytes. While this seemed enormous in the early days of networking, it creates a severe bottleneck on modern high-bandwidth, high-latency networks. Throughout this presentation, we will explore how window scaling works, why it was necessary, and how to configure and verify it in real-world environments. By the end, you will understand how to optimize TCP performance for your specific network conditions. Let me walk you through the diagram that illustrates the evolution of TCP window size requirements. We start with the original TCP design from the 1980s era. This connects to the 16-bit window field, which represents the fixed size allocation in the TCP header. The 16-bit window field leads to the 64 kilobytes maximum window, showing the mathematical ceiling imposed by 16 bits of address space. From the 64 kilobytes maximum window, we see a connection to the problem indicator, which represents the realization that this limit creates performance issues. The problem connects to modern networks with their gigabit speeds and high latency characteristics. Modern networks then leads to the solution, which is window scaling as defined in RFC 1323. This flow demonstrates the logical progression from limitation to solution that we will explore in detail throughout this presentation. The 64 kilobytes window size limitation. Now let us examine why the 64 kilobytes window size becomes a critical limitation. The TCP header contains a 16-bit field for the window size, which can represent values from 0 to 65535. This means the maximum window size is 65535 bytes, or roughly 64 kilobytes. In the early days of TCP, this limit was more than adequate. Network speeds were slow, typically measured in kilobits per second, and network latency was relatively low because most communication happened over local area LANs or short-distance links. However, as networks evolved, this limitation became increasingly problematic. Consider a scenario where you have a 1 gigabits per second connection between two data centers with 50 milliseconds of round-trip latency. With only 64 KB of data in flight, you cannot come close to utilizing the available bandwidth. The mathematics are straightforward. If you can only have 64 kilobytes of unacknowledged data, and it takes 50 milliseconds for the sender to receive an acknowledgement, then in 1 second you can complete 20 round trips. That means the maximum throughput is 64 kilobytes multiplied by 20, which equals 1.28 megabytes per second, or roughly 10 megabits per second. On a 1 gigabits per second link, you would be using only 1% of the available bandwidth. The diagram illustrates how the 64 kilobytes limitation constrains throughput. We begin with a sender that connects to a data pipe element representing the network connection. The data pipe leads to a bottleneck element, which symbolizes the 64 kilobytes window restriction. The bottleneck shows that only a 64 kilobytes window size can be in flight at any moment. From the bottleneck, data flows to the receiver. The receiver sends an acknowledgement represented by the ACK element, which must travel back to the sender. This round trip creates the RTT delay element, representing the time cost of the acknowledgement cycle. The key insight from this diagram is that the bottleneck, not the data pipe capacity, determines actual throughput. Even though the data pipe might have enormous bandwidth capacity, the small window size restricts how much data can be outstanding at any time. Combined with the RTT delay for acknowledgements, this creates a fundamental ceiling on achievable transfer rates regardless of how much bandwidth is available. RFC 1323 Window Scale Option. RFC 1323, titled TCP Extensions for High Performance, introduced the window scale option in 1992 to address the 64 kilobytes limitation. This RFC was authored by Ben Jacobson, Bob Braden, and Dave Borman, who recognized that TCP needed enhancements to perform well on the emerging high-speed networks. The window scale option is elegantly simple in its design. Rather than changing the TCP header format, which would break compatibility with existing implementations, it uses the TCP options mechanism to negotiate a scaling factor during connection establishment. The scaling factor is a power of 2, ranging from 0 to 14. A scale factor of 0 means no scaling, equivalent to traditional TCP. A scale factor of 14 represents the maximum scaling, allowing window sizes up to 1 GB. The actual window size is calculated by taking the value in the window field and shifting it left by the scale factor, which is equivalent to multiplying by 2 raised to the power of the scale factor. For example, if the window field contains 65535 and the scale factor is 7, the actual window size would be 65535 multiplied by 128, which equals approximately 8 megabytes. This allows TCP to support modern high-bandwidth, high-latency networks without any changes to the fundamental header structure. The window scale option is negotiated during the TCP three-way handshake and remains constant for the lifetime of the connection. This means both endpoints agree on their respective scale factors at connection establishment, and these values cannot be changed without closing and reopening the connection. The diagram illustrates the mathematical relationship in window scaling. We start with the TCP window field containing the value 65535, which represents the maximum value storable in 16 bits. This connects to the scale factor element containing the value 7, representing the negotiated scaling multiplier as an exponent. Both the TCP window field and scale factor feed into the calculation element, which shows the formula where the window field is multiplied by 2 raised to the power of the scale factor. The calculation produces the actual window result of 88,480 bytes, which equals approximately 8 megabytes. A separate path shows the maximum scale element with value 14. This connects to max window calculation, which shows 65535 multiplied by 2 to the power of 14. The result flows to maximum window showing 1073725440 bytes, which equals approximately 1 gigabyte. This demonstrates the theoretical maximum window size achievable with window scaling, though practical implementations rarely need windows this large. TCP three-way handshake with window scale. The window scale option is negotiated during the TCP three-way handshake, which is the connection establishment process. Both endpoints must include the window scale option in their initial packets for window scaling to be enabled on the connection. The process begins when the client sends a SYN packet to initiate the connection. Within this SYN packet, the client includes a window scale option specifying its desired scale factor. The client also sets an initial window size in the TCP header, which at this point is not yet scaled. The server responds with a SYN ACK packet. If the server supports window scaling and wishes to use it, it includes its own window scale option in the SYN ACK. The server's scale factor may be different from the client's, as each direction of the connection can use a different scale factor. The client completes the handshake with an ACK packet. From this point forward, all window values advertised by the client are scaled by the server's scale factor, and all window values advertised by the server are scaled by the client's scale factor. It is crucial to understand that window scaling must be negotiated during the initial handshake. If either endpoint does not include the window scale option, or if a middlebox strips the option from the packets, window scaling will not be used for that connection. This is a common source of performance problems when firewalls or NAT devices improperly handle TCP options. The sequence diagram shows the complete three-way handshake with window scale negotiation between a client and server. The interaction begins when the client sends a SYN packet to the server. This packet includes the WS equals 7 option, indicating the client wants to use a scale factor of 7, along with window equals 65535 showing the initial unscaled window advertisement. The server processes this and responds with a SYN ACK packet back to the client. This response includes WS equals 8, showing the server has chosen its own scale factor of 8, which differs from the client's choice. The server also includes its window equals 65535 initial advertisement. At this point, both sides have exchanged their scaling preferences. The client completes the handshake by sending an ACK packet to the server. This acknowledgement includes window equals 32768, which is now the first scaled window advertisement. A note indicates that from this point forward, all window values sent by the client use the server's scale factor of 8 for scaling, and all window values sent by the server use the client's scale factor of 7. This asymmetric arrangement allows each direction of data flow to be optimized independently based on each endpoint's buffer capacity and network conditions. Common window scale values in practice. In real-world deployments, you will encounter various window scale factors depending on the operating system, network configuration, and application requirements. Understanding typical values helps you identify whether connections are properly optimized. Linux systems commonly use scale factors between 6 and 10, depending on the configured buffer sizes. The default maximum receive buffer on modern Linux distributions is typically 4 to 6 megabytes, which requires a scale factor of around 7. Systems configured for high bandwidth transfer may use scale factors up to 10 or higher. Windows systems historically used more conservative scale factors, often in the range of 2 to 4. However, modern versions of Windows have improved their TCP stack and now use scale factors comparable to Linux when auto-tuning is enabled. BSD-based systems, including Mac OS, typically use moderate scale factors around 6 to 8. These systems have well-tuned default buffer sizes that balance memory usage with performance. Some specialized systems and embedded devices may use a scale factor of 0, effectively disabling window scaling. This is sometimes done intentionally to reduce memory usage or to work around compatibility issues with certain network equipment. The table in this slide shows reference values for common configurations. Benefits of window scaling. Window scaling provides substantial benefits for modern network performance. The primary advantage is enabling TCP to fully utilize high bandwidth, high latency network paths that would otherwise be severely bottlenecked by the 64 kilobytes limit. With proper window scaling, a single TCP connection can achieve throughput limited only by the available bandwidth and the endpoint processing capabilities. This is particularly important for bulk data transfers, database replication, backup operations, and other scenarios involving large amounts of data. Window scaling also improves the efficiency of network resources. When connections can maintain higher throughput, transfers complete faster, freeing up bandwidth for other traffic. This benefits both the endpoints involved and the network infrastructure as a whole. Another benefit is reduced connection count. Without window scaling, applications might need to open multiple parallel connections to achieve acceptable aggregate throughput. With window scaling, a single connection can often achieve the same or better performance, reducing connection management overhead and simplifying application design. Window scaling works transparently with other TCP optimizations like selective acknowledgements, SACK, and TCP timestamps, which were also introduced in RFC 1323. Together, these enhancements make TCP suitable for the demands of modern high-speed networks. The diagram compares throughput with and without window scaling across different network scenarios. The structure shows without scaling scenarios branching to their throughput results, followed by with scaling scenarios with their improved results. Starting with the scenarios without scaling, we see LAN without scaling connects to LAN throughput no scale showing 640 megabits per second achievable, which is good since LAN latency is low enough that the 64 kilobyte limit does not severely constrain performance. WAN without scaling connects to WAN throughput no scale showing only 10 megabits per second achievable due to the higher latency, making the 64 kilobyte limit a severe bottleneck. Satellite without scaling connects to SAT throughput no scale showing a mere 0.8 megabits per second because the extreme latency of satellite links makes the 64 kilobyte limit devastating to performance. Now examining the scenarios with scaling enabled, LAN with scaling connects to LAN throughput scaled showing 1 gigabits per second, representing full link utilization with minimal improvement needed since LAN was already performing reasonably. WAN with scaling connects to WAN throughput scaled showing 1 gigabits per second achievable, a dramatic 100x improvement over the unscaled case as the larger windows can fill the high bandwidth pipe despite the latency. Satellite with scaling connects to SAT throughput scaled showing 100 megabits per second achievable, an enormous 125x improvement that makes satellite links actually usable for data transfer by allowing enough data in flight to overcome the 600 milliseconds round-trip delay. The key insight from this comparison is that window scaling provides the greatest benefit on high-latency links, where it can improve throughput by orders of magnitude, while still providing meaningful improvements on lower latency connections. Verifying window scale with packet captures. Now that we understand the theory behind window scaling, let us examine how to verify it in practice using packet capture tools. Wireshark and tcpdump are the primary tools for analyzing TCP options, including window scale factors. When capturing the initial TCP handshake, you can observe the window scale option in the SYN and SYN-ACK packets. In Wireshark, this appears in the TCP options section of the packet details pane. The option is identified by kind value 3 and includes a single byte indicating the scale factor. It is important to capture the connection establishment phase to see window scaling negotiation. If you start capturing after the handshake completes, you will only see the scaled window values without knowing what scale factors are in use, making it impossible to determine the actual window sizes. Wireshark has a helpful feature that automatically calculates the true window size when it has observed the handshake. It displays both the raw window value from the packet and the calculated window size based on the negotiated scale factor. Analyzing window scale in Wireshark. Let us examine the specific details you will see when analyzing window scale in Wireshark. The TCP options section reveals crucial information about window scaling configuration and can help diagnose performance problems. In the packet details, look for the options field within the TCP header. The window scale option has a kind value of 3, a length of 3 bytes, and contains the shift count, which is the scale factor. Wireshark displays this in a human-readable format showing the scale factor and the resulting multiplier. For packets after the handshake, Wireshark shows both the window size value, which is the raw 16-bit value from the packet header, and the calculated window size, which applies the appropriate scale factor. The calculated value is what you should use when analyzing throughput and buffer utilization. You can also use Wireshark's display filters to focus on packets with window scale options. The filter tcp.options.wscale exists will show only packets containing the option, which are the SYN and SYN-ACK packets. This is useful when analyzing large captures to quickly locate the handshake. Using tcpdump for window scale analysis. While Wireshark provides an excellent graphical interface, tcpdump is invaluable for command line analysis, especially on remote servers where graphical tools are not available. tcpdump can display window scale options with the appropriate verbosity flags. The key to seeing TCP options in tcpdump output is using the verbose flag. With the double verbose flag, tcpdump shows the window scale option in the SYN and SYN-ACK packets. The output format shows the option as W-scale followed by the scale factor value. You can combine tcpdump filters to capture only the TCP handshake packets, reducing the amount of data you need to analyze. Filtering for SYN packets using the TCP flags filter captures exactly the packets containing window scale negotiations. For ongoing monitoring, tcpdump can write to a file in PCAP format, which you can later analyze with Wireshark on a workstation with graphical capabilities. This workflow is common when troubleshooting production servers. Let me walk through the tcpdump commands shown in the code block. The first command is tcpdump with the -i eth0 flag, which specifies the network interface to capture on. The eth0 value is the first Ethernet interface on most Linux systems. The -nn flags prevent DNS and port name resolution, showing raw IP addresses and port numbers for faster output and clearer analysis. The -vv flag enables very verbose output, which is essential because window scale options only appear at this verbosity level. The port 443 filter restricts capture to traffic on port 443, which is HTTPS, reducing the volume of captured packets to only what we are interested in. The comment shows example output for a SYN packet. The timestamp 15 hours 23 minutes and 45 seconds. 123456 marks when the packet was captured. The IP header shows the source 10.0.1.100.54321 connecting to destination 172.16.0.50.443. The flags S indicates this is a SYN packet. The Win65535 portion shows the advertised window size. The options section includes MSS1460 for maximum segment size, SAC OK indicating selective acknowledgement support, TS val and ECR showing TCP timestamps, NOP for padding, and critically W scale 7 revealing the window scale factor. The linked 0 at the end indicates no payload data, which is expected for a SYN packet. The second command adds capture.pcap to write packets to a file instead of displaying them. Linux kernel TCP buffer parameters. Linux provides several kernel parameters that control TCP buffer sizes and directly affect window scaling behavior. Understanding these parameters is essential for optimizing TCP performance on Linux systems. The primary parameters are net.ipv4.tcp_rmem and net.ipv4.tcp_wmem, which control receive and send buffer sizes respectively. Each parameter accepts three values representing the minimum, default, and maximum buffer sizes in bytes. The minimum value sets the floor for buffer allocation, ensuring each connection has at least this much buffer space. The default value is used for new connections under normal conditions. The maximum value sets the ceiling that TCP autotuning can reach when it detects high bandwidth delay product conditions. The kernel automatically calculates the window scale factor based on the maximum receive buffer size. If you increase TCP_or mem maximum, the kernel will negotiate a larger scale factor to accommodate the larger potential window size. There are additional parameters that influence buffer behavior. The net.core.or_mem_max and net.core.wem_max parameters set absolute ceilings on buffer sizes that apply to all sockets, not just TCP. The TCP-specific maximums cannot exceed these core limits. Configuring TCP buffers on Linux. Configuring TCP buffers on Linux involves setting kernel parameters either temporarily using sys control commands or permanently through configuration files. Let us examine the practical steps for optimizing these settings. For temporary changes that do not survive a reboot, use the sysctl command with the -w flag to write new values. This is useful for testing different configurations before making permanent changes. You can immediately verify the new values using sysctl without the right flag. For permanent configuration, add the parameter settings to a file in the /etc/sysctl.d/ directory or to the main /etc/sysctl.configuration file. Files in sysctl.d are processed in alphabetical order, so using a numbered prefix like 99 ensures your custom settings are applied last and override any defaults. When tuning buffer sizes, consider your network's bandwidth delay product and add overhead for processing. A common starting point is to set the maximum receive buffer to 2 times the largest bandwidth delay product you expect to encounter. Monitor connection performance and adjust as needed. Let me explain each command in the code block sequentially. The first command sysctl space wnet.ipv4.tcp_rmem sets the receive buffer parameters. The equals sign followed by 40961317262911456 provides 3 space-separated values. The first value 4096 sets the minimum buffer at 4 kilobytes, ensuring every connection gets at least this much memory. The second value 131072 sets the default at 128 kilobytes, which is used for new connections under normal memory conditions. The third value 629146 sets the maximum at 6 megabytes, which is the ceiling for TCP autotuning. The second command sysctl-wnet.ipv4.tcp_wmem follows the same pattern for send buffers. The third command sysctl-wnet.core.rmem max equals 629145 sets the absolute ceiling for receive buffers at 6 megabytes. This core parameter must be at least as large as TCP_rmem maximum. Otherwise the TCP setting is effectively capped at the lower core limit. The fourth command sysctl-wnet.core.wmem_max equals 4194304 similarly sets the send buffer ceiling at 4 megabytes. Again, this must accommodate the TCP_wmem maximum value. The comment block shows how to make these settings permanent. The echo command with append redirection sends the setting to a configuration file. The final command sysctl-p/etc/sysctl.d/99-tcp-tuning.configuration applies the settings from the specified file immediately. The -p flag tells sysctl to read and apply values from the given configuration file without requiring a reboot. Windows TCP stack configuration. Windows operating systems have their own TCP implementation with different configuration approaches than Linux. Understanding Windows TCP tuning is important for mixed environments and Windows-based server deployments. Modern Windows versions, starting with Vista and Server 2008, include Receive Window Auto-Tuning, which is Microsoft's implementation of automatic buffer sizing. This feature dynamically adjusts the receive window based on network conditions, similar to Linux auto-tuning. Windows auto-tuning has several configuration levels: disabled, highly restricted, restricted, normal, and experimental. The normal setting is the default and works well for most scenarios. The experimental setting allows the most aggressive buffer growth but may cause issues with some network equipment. Configuration is done through the netshish command line utility or PowerShell commandlets. The netshish interface TCP commands provide access to TCP global parameters, while get net TCP setting and set net TCP setting PowerShell commandlets offer more granular control in Windows 8 and later. Unlike Linux where you set explicit buffer sizes, Windows uses a more abstracted approach with tuning levels. This simplifies configuration but provides less precise control. For most deployments, the default settings work well, but high-performance applications may benefit from the experimental or restricted levels depending on network conditions. Let me walk through the commands in the code block. The first command netshish interface TCP show global displays the current TCP global settings. The netshish utility is Windows Network Shell for configuration. The interface TCP portion targets TCP interface settings, and show global displays all global TCP parameters including the auto-tuning level, congestion provider, and other settings. The sample output shows key parameters. Receive window auto-tuning level equals normal indicates the default auto-tuning mode is active. Add-on congestion control provider equals CTCP shows compound TCP is the congestion control algorithm. ECN capability equals disabled shows explicit congestion notification is off. Receive segment coalescing state equals enabled indicates the kernel will combine small receives for efficiency. Timestamps equals enabled shows TCP timestamps are active, which work alongside window scaling. The next command netshish interface TCP set global auto-tuning level equals experimental changes the auto-routing to its most aggressive mode. The auto-tuning level parameter accepts values from disabled through experimental. The experimental level allows the largest receive windows but may cause compatibility issues with certain firewalls or network equipment that do not properly handle large windows. The PowerShell section shows an alternative approach. GetNet TCP setting retrieves TCP settings using the newer PowerShell CMD-led interface. This provides more detailed output and is the preferred method on Windows 8, Server 2012, and later. The setNet TCP setting command with setting name Internet Custom targets a specific TCP profile. The auto-tuning level local experimental parameter sets aggressive auto-tuning for that profile. Windows uses different profiles for different network types, so you may need to configure multiple profiles depending on your connection types. Diagnosing window scale problems. When TCP connections exhibit poor throughput despite adequate bandwidth, window scaling problems should be high on the list of suspects. A systematic diagnostic approach helps identify whether window scaling is functioning correctly. Start by capturing packets at both endpoints during connection establishment. Compare the SYN and SYN-ACK packets to verify that both contain window scale options and that the options arrive intact at each endpoint. Any discrepancy indicates a middlebox is modifying or stripping the options. Next, examine the window values during bulk data transfer. Calculate the actual window size using the negotiated scale factors and compare to the bandwidth delay product. If the actual window is significantly smaller than the BDP, the connection cannot achieve full throughput. Check for window-limited conditions by looking for patterns where the sender stops transmitting even though the link is not congested. This appears in packet captures as gaps in transmission followed by new data only after acknowledgements arrive. Wireshark's TCP stream graphs can visualize this pattern clearly. Also verify that buffer sizes on both endpoints are appropriately configured. Even with window scaling, if the maximum buffer is too small for the BDP, throughput will be limited. Use the operating system tools we discussed earlier to check and adjust buffer settings. The diagram presents a systematic diagnostic flowchart. The process starts at begin diagnosis, which leads to capture both ends, indicating you should take packet captures at both client and server. This flows to compare SYN packets, where you analyze the captured handshakes. Compare SYN packets leads to the decision WS options match asking whether the window scale options are identical at both capture points. If they do not match, the flow goes to middlebox problem, which connects to fix or bypass indicating you need to reconfigure or avoid the problematic device. If the WS options match, the flow continues to check window sizes, where you verify the actual window values during data transfer. This leads to the decision window equals BDP asking whether the window size is at least as large as the bandwidth delay product. If the window is smaller than BDP, the flow goes to buffer too small, which connects to increase buffers indicating you need to adjust the TCP underscore or mem or equivalent settings on the appropriate endpoint. If the window matches BDP, the flow continues to check for stalls, examining whether data transfer pauses unexpectedly. The decision sender waiting asks whether the sender stops transmitting while waiting for acknowledgements. If the sender is waiting, this indicates window limited condition, which connects to investigate further for deeper analysis of why the window is not growing as expected. If the sender is not waiting but throughput is still low, the flow reaches other issue, indicating the problem lies elsewhere such as congestion, packet loss, or CPU limitations rather than window scaling. Testing window scale with iPerf3. iPerf3 is an excellent tool for testing TCP performance and verifying that window scaling is working correctly. It allows you to set specific buffer sizes and measure the resulting throughput, making it ideal for diagnosing and tuning window scaling configurations. Real-world performance optimization. Now let us examine how window scaling applies to real-world performance optimization scenarios. Understanding when and how to tune window scaling settings can make the difference between acceptable and excellent network performance. The first step in any optimization effort is measuring baseline performance. Before changing any settings, document current throughput using tools like iPerf3. Measure round-trip times with ping or dedicated latency measurement tools, and capture sample traffic to observe current window scaling behavior. Once you have baseline measurements, calculate the bandwidth delay product for your network paths. Remember that BDP equals bandwidth multiplied by round-trip time. For a 10 gigabits per second link with 20 milliseconds of RTT, the BDP is 10 billion bits per second times 0.020 seconds, which equals 200 million bits or 25 megabytes. Your target buffer size should be at least equal to the BDP, and many practitioners recommend 2 times BDP to account for variations in processing delays. With a 25 megabyte BDP, you would want receive buffers of at least 50 megabytes, requiring a window scale factor of 10 or higher. After making configuration changes, repeat your measurements to verify improvement. Performance tuning is iterative, and you may need to adjust settings based on observed results. Also monitor for any negative effects like increased memory usage or interaction with other traffic on shared links. The diagram illustrates the performance optimization workflow as a cyclical process. We begin at start optimization, which leads to measure baseline where you capture initial performance metrics including throughput and latency. From measure baseline, the flow continues to calculate BDP, where you compute the bandwidth delay product for your network path. Calculate BDP leads to compare to current, where you evaluate whether existing buffer settings match the calculated BDP requirements. This flows to the decision point buffers adequate, which asks whether current buffer sizes are sufficient for the BDP. If buffers are adequate, the flow proceeds to check throughput, where you verify the connection is achieving expected performance. This leads to another decision at target met asking whether throughput goals are achieved. If the target is met, the flow reaches optimization complete, indicating the tuning process is finished. If the target met check fails, meaning throughput is below expectations despite adequate buffers, the flow goes to investigate other factors. This leads to check for loss congestion CPU, representing the need to examine packet loss, network congestion, or CPU bottlenecks that may limit performance independent of window scaling. Returning to the buffer's adequate decision, if buffers are not adequate, the flow goes to increase buffer size, where you adjust TCP_RMEM and related parameters. From there, the flow continues to update scale factor, reflecting that larger buffers may require higher window scale values. Update scale factor loops back to measure baseline, creating the iterative optimization cycle where you re-measure after each change to verify improvement. Data center and high-performance computing. Data center environments present unique challenges and opportunities for TCP window scaling optimization. With high bandwidth, low latency networks inside the data center and potentially high latency connections to remote sites, careful tuning is essential. Within a data center, latencies are typically very low, often under 1 millisecond. This means the BDP is relatively small even for 100 gigabits per second links. A 100 gigabits per second link with 0.5 milliseconds RTT has a BDP of only 6.25 megabytes. However, connections between data centers or to cloud regions can have significant latency, dramatically increasing BDP. High-performance computing environments often require aggressive tuning. HPC applications may transfer terabytes of data between compute nodes and storage systems, where even small percentage improvements in throughput translate to significant time savings. Scale factors of 10 to 14 are common in these environments. Storage systems including network-attached storage, storage area network over IP, and object storage backends benefit greatly from window scaling optimization. These systems often serve multiple clients simultaneously, so buffer settings must balance per connection performance against total memory consumption across all connections. Consider using dedicated network paths for bulk data transfer when possible. Quality of service settings can ensure high bandwidth flows get appropriate buffer allocation without impacting latency-sensitive traffic on the same infrastructure. Cloud provider considerations -AWS. When deploying applications in Amazon AWS, understanding how AWS infrastructure interacts with TCP window scaling helps optimize performance. AWS provides several features that affect TCP behavior, and there are specific considerations for different instance types and network configurations. AWS uses enhanced networking with Elastic Network Adapter, or ENA, on most modern instance types. ENA supports TCP window scaling and provides high throughput with low latency within AWS regions. However, cross-region and internet-facing traffic has higher latency requiring larger windows. EC2 instances have network performance tiers based on instance size. Larger instances like the C5N.18x large can achieve 100 gigabits per second network throughput, while smaller instances may be limited to 5 or 10 gigabits per second. Your buffer settings should match the maximum throughput your instance type can achieve. Amazon Linux 2 and newer Amazon Linux versions come with reasonable TCP defaults, but may still benefit from tuning for specific workloads. The default TCP or MEM maximum is typically around 6 megabytes, which may be insufficient for high-throughput cross-region transfers. For connections through AWS Global Accelerator or CloudFront, be aware that these services terminate TCP connections at edge locations, potentially affecting observed window scaling behavior. The TCP parameters that matter are those on the edge-to-origin connection, which AWS manages separately. Let me explain the commands shown for AWS optimization. The first command cat/proc/sys/net/IPv4/TCP_RMEM reads the current receive buffer settings directly from the proc file system. This shows the live kernel values without using sysctl. The expected output 409613107262914556 shows minimum, default, and maximum values in bytes. The second command ethtool-i eth0 queries the network interface driver information. The ethtool utility provides hardware and driver details. The third command demonstrates setting optimized buffer values. The fourth command sysctl-wnet.ipv4.tcp_wmem equals 409652428816777216 applies the same values to send buffers. The final command syscontrol-wnet.core.or/mem max equals 16777216 sets the core receive buffer maximum to match the TCP maximum. Without this setting, the TCP_or/mem maximum would be capped at the lower core limit, preventing the larger buffers from being used. Container and Kubernetes networking. Container environments introduce additional complexity for TCP window scaling because containers typically share the host's network stack, and network policies or overlays can affect TCP behavior. Understanding these interactions is crucial for optimized container networking. In Docker and similar container runtimes, containers inherit the host's kernel TCP parameters by default. Changes to TCP or mem on the host affect all containers running on that host. This simplifies tuning but means you cannot have different settings for different containers without additional configuration. Kubernetes clusters often use overlay networks like Flannel, Calico, or Cilium that encapsulate pod-to-pod traffic. This encapsulation adds overhead and can affect maximum segment size, but generally does not interfere with window scaling. However, network policies that drop or modify packets could potentially impact TCP options. When pods communicate across nodes, the path includes the container network namespace, the host network stack, the physical or virtual network, and the receiving host and container namespaces. Each hop processes TCP packets, and the host kernel parameters govern window scaling behavior at each point. For Kubernetes, you can tune TCP parameters on worker nodes using daemon sets that apply sysctl settings at boot, or through node configuration management tools. Some container network interfaces also support tuning through their configuration, though this varies by CNI implementation. TCP offload and window scaling. Modern network interface cards offer TCP offload capabilities that move certain TCP processing tasks from the CPU to dedicated hardware. Understanding how these features interact with window scaling helps ensure optimal performance and avoid potential issues. Large Receive Offload, or LRO, aggregates multiple incoming TCP segments into larger chunks before passing them to the kernel. This reduces CPU overhead but can interact with window scaling by changing how the kernel perceives segment boundaries. Generic Receive Offload, GRO, provides similar benefits with better software compatibility. TCP Segmentation Offload, or TSO, allows the kernel to pass large buffers to the NIC, which then segments them into proper TCP packets. This dramatically reduces CPU cycles spent on packet creation. TSO works well with large window sizes because it can efficiently handle the larger data volumes enabled by window scaling. Receive Side Scaling, RSS, distributes incoming traffic across multiple CPU cores using hash-based flow distribution. When troubleshooting performance issues, temporarily disabling offload features can help isolate whether the issue is with TCP tuning or offload behavior. Use ethtool to check and modify offload settings on Linux systems. The diagram illustrates how TCP offload features process data alongside window scaling. The flow begins with application data representing the data to be transmitted. This connects to the kernel TCP stack where TCP processing normally occurs. From the kernel TCP stack, the path branches based on offload capabilities. One branch leads to the decision TSO enabled, asking whether TCP segmentation offload is active. If TSO is enabled, the flow goes to large segments to NIC, indicating the kernel sends large unsegmented data to the network card. Large segments to NIC connects to NIC hardware segmentation, where the network interface card segments the data into proper TCP packets. The resulting output is wire packets representing properly formatted TCP segments. If TSO is not enabled, the kernel TCP stack must perform kernel segmentation, manually dividing data into TCP segments before sending to the NIC. This path also reaches wire packets but with higher CPU cost. On the receive side, wire packets enter the system and reach another decision point LRO/GRO enabled, asking whether receive offload is active. If enabled, the flow goes to aggregate segments where either hardware LRO or software GRO combines multiple small packets into larger chunks. Aggregate segments then delivers large buffers to kernel, reducing per packet processing overhead. If receive offload is disabled, packets go through individual packet processing where each packet is handled separately by the kernel. Both paths eventually deliver data to the application data received endpoint. but the offloaded path does so with significantly less CPU utilization, especially important when large windows result in high packet volumes. Window scaling with IPv6. IP version 6 networks support TCP window scaling identically to IP version 4, as window scaling is a TCP layer feature independent of the IP version. However, there are some practical considerations when working with IP version 6 that affect overall TCP performance alongside window scaling. IP version 6 headers are larger than IP version 4 headers, 40 bytes versus 20 bytes minimum, which slightly reduces the maximum segment size for a given MTU. With standard 1500-byte Ethernet MTU, IP version 6 TCP segments have about 20 bytes less payload than IP version 4. This marginal difference has minimal impact on window scaling effectiveness. Path MTU discovery is essential for IP version 6 since IP version 6 prohibits router fragmentation. If PMTUD fails and the sender uses packets that are too large, they will be dropped rather than fragmented. This can appear similar to window-related issues but is actually an MTU problem. Proper PMTUD ensures TCP can use optimal segment sizes alongside large windows. IP version 6 extension headers, if present, further reduce payload capacity. While extension headers are uncommon in typical traffic, applications using IPsec or other extensions should account for the overhead when calculating effective bandwidth for BDP calculations. Linux uses the same TCP_/mem and TCP_WMem parameters for both IPv4 and IPv6 TCP connections. There are no separate IPv6 specific buffer settings. Configuration changes apply equally to both protocol versions. The diagram compares the packet structures of IP version 4 and IP version 6 with TCP. The IP version 4 path begins with IP version 4 header at 20 bytes minimum, which leads to TCP header at 20 bytes plus options. The TCP header connects to payload maximum showing 1460 bytes with standard 1500-byte MTU. A note indicates the calculation where 1500 MTU minus 20 IP minus 20 TCP equals 1460 bytes of payload. The IP version 6 path shows IP version 6 header at 40 bytes fixed, leading to TCP header similarly at 20 bytes plus options. The payload maximum for IP version 6 shows 1440 bytes. The corresponding calculation shows 1500 MTU minus 40 IP minus 20 TCP equals 1440 bytes. Both paths converge at the window scaling element, which leads to same TCP parameters. Monitoring window scale in production. Effective production monitoring of TCP window scaling helps identify performance issues before they impact users. Several tools and techniques enable ongoing visibility into window scale behavior across your infrastructure. The Linux SS command provides socket statistics including window scale information for established connections. Unlike netstat, SS reads directly from kernel data structures and shows scaled window values. The -i flag adds internal TCP information including the window scale factors. For continuous monitoring, tools like Prometheus with the node exporter can collect TCP statistics over time. While these do not capture per connection window scale factors, they provide aggregate metrics on TCP performance and buffer usage that indicate whether tuning changes are having the desired effect. Network monitoring systems that capture flow data or perform deep packet inspection can track window sizes across your infrastructure. This enterprise-level monitoring is particularly valuable for identifying middleboxes that interfere with window scaling or connections that consistently underperform. Application performance monitoring tools often include TCP-level metrics in their traces. These can correlate slow application responses with TCP connection characteristics, helping identify when window-limited throughput causes user-visible performance problems. Let me walk through the monitoring commands in the code block. The first command ss -ti displays detailed TCP socket information. The SS utility is the modern replacement for netstat. The -T flag limits output to TCP sockets. The -I flag adds internal TCP information including window scaling details. The example output shows connection details. The ESTAB state indicates an established connection. The addresses show local 192.168.1.100 port 543 connected to remote 10.0.0.50 port 443. The cubic label identifies the congestion control algorithm. The W-scale 7.8 shows the window scale factors where 7 is used for received windows and 8 for sent windows. The RTO204 shows the retransmission timeout in milliseconds. The RTT value 25.5/12.3 shows round-trip time and variance. The CWND42 shows the congestion window in segments. The send rate shows calculated throughput capacity. The second command SST state established filters to only established connections using the state filter. This excludes listening sockets and connections in other states, focusing on active data transfer connections. The third command uses grep to extract W-scale values specifically. The pipe to sort and unique-C provides a count of each unique W-scale combination seen. This is useful for understanding the distribution of window scale factors across your connections and identifying any connections using unexpectedly low values. The fourth command cat/proc/net/sockstat displays socket statistics from the proc file system. The output shows TCP with in-use count of current connections, orphan count of connections without parent process, TW for time wait count, alloc for allocated sockets, and mem showing TCP memory pages in use. Best practices and recommendations. Let us conclude with a summary of best practices for TCP window scaling that will help you optimize network performance while avoiding common pitfalls. These recommendations are based on years of operational experience and apply across most environments. Always measure before tuning. Collect baseline metrics including throughput, latency, and current window scale factors before making any changes. This allows you to verify improvements and identify any regressions. Optimization without measurement is just guessing. Size your buffers based on calculated BDP with margin. A buffer maximum of 2 times BDP provides headroom for variations in network conditions and processing delays. Excessively large buffers waste memory and can increase latency due to buffer bloat, while undersized buffers limit throughput. Use TCP autotuning where possible. Modern operating systems do a good job of adjusting buffers dynamically. Manual tuning should focus on setting appropriate maximums that autotuning can grow into, rather than trying to set fixed optimal values. Test with realistic workloads. Synthetic benchmarks like iPerf3 are useful for measuring maximum capability, but real application behavior may differ. Verify that tuning improvements translate to actual application performance gains. Document your configuration. Record what settings you changed, why you changed them, and what improvement you observed. This documentation is invaluable when troubleshooting future issues or replicating the configuration on new systems. The diagram summarizes the best practices workflow. The process begins at start with defaults using the operating system's default TCP configuration. This leads to measure performance where you establish baseline throughput and latency metrics. Measure performance connects to calculate BDP for your specific network paths. Calculate BDP flows to the decision compared to defaults asking whether default buffer sizes are adequate for your BDP requirements. If defaults are adequate, the flow proceeds to enable autotuning if not already active, which leads to monitor ongoing for continuous performance verification. Monitor ongoing loops back to measure performance, creating a continuous monitoring cycle. If defaults are not adequate, the flow goes to increase buffer maximums to accommodate your calculated BDP. This leads to test with iPerf for validation using synthetic benchmarks. From there, the flow continues to test with application verifying real workload performance. Test with application leads to the decision performance acceptable, asking whether the changes achieve the desired improvement. If not acceptable, the flow goes to investigate issues, which could include middlebox problems, CPU limitations, or other factors. Investigate issues connects to adjust and retry, which loops back to test with iPerf for another validation cycle. If performance is acceptable, the flow proceeds to document changes, recording what was modified and the observed results. Document changes then connects to monitor ongoing, joining the continuous monitoring cycle. This complete workflow ensures systematic optimization with proper validation and documentation at each step. Thank you for your attendance. Please consider subscribing to the channel and liking this video.